Hello, my name is Ryan Sacko. This is a re-recording of IMDRC's Journal Club, which was hosted by Jane Clark. I am one of the two Halverson Award winners, which is the reason why I was invited to this to give this presentation. And I hope that this re-recording suffices, hopefully, for our archives and records as we move forward here. I will also try to address the questions that I remember that were provided throughout the presentation. And I thank everyone who was in attendance, and I thank everyone who has taken the time to watch this recording as it is posted and kept here moving forward. Before I get rolling here, the title of my presentation is No Story is a Straight Line. This is a homage to Pat Conroy, who is an author, who is also a Citadel graduate, Citadel being the institution where I currently work. I think it is well related to both motor development, our path through life, throughout the lifespan. I also think that it is a nice homage to many people's paths to a PhD, through a PhD, and more importantly, to how we answer a question in motor development. Before I go any farther, I wanted to thank all of my co-authors. There's a lot of heavy lifting in authorship, in research studies that has to happen for things to be published. And I wouldn't be sitting here giving this presentation today if it wasn't for everyone that's listed here, most notably David Stodden, who is my mentor, who was the reason that I pursued the PhD that I did, and a reason for a whole heck of a lot more from a career standpoint as well. So thank you, David Stodden. Also, thank you to all of the GAs, research assistants, current co-authors that are not related to current publications, but will be in the future. Thank you for all of your hard work and really helping to lift me up for something like this in this presentation, and as a recipient of the Halverson Award. So no path is a straight line. In this case, I actually want to present two different papers. These were available to individuals ahead of the Journal Club to review. I want to talk about the process in terms of how these two papers came about, one being energy expenditure of discrete movement skills, and the other one actually being developmental sequences of kicking. So before we kind of get into those two papers, I want to set up a little bit here of what we knew ahead of time. And what we do know, we have a really great understanding of, is continuous activities like walking and running. This goes as far back as the Douglas bag technique, in which we would actually capture all of the air that you would breathe during exercise and measure it for its the gas components, oxygen, CO2, etc. And all the way up to med carts today. Many of you have probably worked with them in a physiology lab during your education at some point. And we have a wonderful understanding of our overall physiology during continuous activities. What we don't have a good understanding of is discrete skills, things like kicking, throwing, and striking. We have some understanding, and we have a somewhat of an understanding of what happens during gameplay that involves these skills, like playing for Americans soccer, and for non-Americans football, or baseball, cricket, etc. And that's really where a lot of my research initiated, where it started, and where I'd like to take this talk today is to talk about some of that research. So the first thing I want to set up here is the methods that went into to looking at this. So what we did was we looked at a sample of adults and later a sample of children. The adults were an average age of about 24 years old, they're young adults, and the children were an average age of 8. So 7 to 9-year-olds was the criteria. We did this to avoid pubescence, meet people ahead of pubescence. And what we did was we did 5 kicks, we did 5 throws, we did 5 strikes for 9 minutes in 3 different interval conditions. So we did a 30-second interval, a 12-second interval, and a 6-second interval. So for everyone watching this recording, I just want you to take a moment and think to yourself, if I'm going to kick a ball, throw it or strike it as hard as I can once every 30 seconds, what is that going to do? Is it going to raise your heart rate? Is it not going to raise your heart rate? Take a look. This is actually what we did. And I love long, awkward pauses. Um, and the reason being, this is a long time. What can you do in this amount of time? What can you convey to the learner? So think about all the information that you can give once every 30 seconds if you're taking something like this. Also, think about how often in a sports setting, in a school setting, you actually have a line of way too many kids. Kids are waiting way longer than 30 seconds. All right, so this represents the 12-second interval. And then again, what they would do is uh, every 12 seconds, they would either kick, so 5 times in a row, throw 5 times in a row, strike 5 times in a row, and they would repeat that over and over again for minutes. And what we're trying to actually achieve is steady state. So over the course of the first few minutes, you'll see heart rate rise, energy expenditure rise, and then you'll hit a steady state. So this individual is wearing a Cosmed K4B2. This is actually a portable metabolic cart. It can be worn as a backpack. Some of you may come in contact with this or other versions of it. Currently, the more up-to-date version of this is a Cosmed K5. And again, it allows freedom of movement in a three-dimensional space, and you can actually take it outside if you needed to. So this is once every 6 seconds. If you think about doing something like throwing, kicking, striking every 6 seconds for 9 minutes, I think everybody here understands that that's something that can be pretty intense. But some of the things that we're going to be talking about here is the variance in the skill levels across all of our individuals. This is somebody who is kind of a median value in terms of our process-oriented skill, as well as product in terms of speeds that he was producing. They're using a foam ball. It's a safety precaution. Same thing with the tennis balls. The tennis balls have a little bit of give to them to make sure as they came off the wall, we wouldn't have a problem. So again, I love interaction. I'd love everyone to just think for a minute here before I give the results. This is the adult study. You watching this, probably an adult. If you were to throw every, in this case, we're going to talk about 6 seconds burst every 6 seconds, would your energy expenditure actually cross the thresholds for moderate to vigorous physical activity? So the first line here I'm putting there is 6 METs. So 6 METs is the threshold for vigorous activity in adults, and 3 METs, the red line there, is the threshold for moderate activity in adults. Now, what does that mean? If you're sitting still, like you might be right now, you're at 1 MET, so metabolic equivalent of task is just 1. If you got up and walked briskly down the hallway, you'd be at a 3. So that would be that threshold of moderate activity. That'd be your comparison. And if you were at a 6 or above, you'd be sprinting down the hallway, right? So what do you think? Once every 6 seconds? Both are males and female adults. It was much higher. At our 12-second interval, okay, we were at a moderate level, because we hadn't quite crossed that threshold yet of vigorous for females like we did for males. Now here's the one. Once every 30 seconds, the one where you're standing in line with 4 other kids and you're waiting for your turn, or the one where you're sitting there getting instruction from your coach, your teacher to participate again for 30 seconds. That long awkward pause, was that enough to cross the barrier for moderate to vigorous physical activity in adults? It was, and that was surprising to us as well. We actually set that up to be a control group, and it turns out that was enough. So what does this mean? What does this mean towards practitioners and interventions and so forth? Have a timer. Make sure something goes off every 30 seconds to remind people that they should be participating in the repetition that they need. Don't let them sit off to the side for minutes on end. Once every 30 seconds, and you're crossing that threshold to moderate to vigorous physical activity. This research at the time was also related to accelerometers, and if those accelerometers were picking that up, I'll let you read those papers to find the answer. So what about in kids? So think again. So kids, the lines are a little different here. They're going to be at 7 METs, okay, for children, and the threshold for MVPA, the moderate side, is going to be at 4. Now, a lot of the older research that you might find with Ainsworth et al., which is a repository for all of the energy expenditure knowledge that has been published to this point, some of that older research uses 3 and 6 instead of 4 and 7 METs as the threshold for children. These kids are between the ages of 7 and 9 years old, so we absolutely want to use 4 METs as that threshold instead of 3. But for the 6-second interval, is that going to be enough? Well, the results were very similar to the adult study in that both boys and girl groups were above that vigorous line. It looked the same at the 12 range interval, and then 30 seconds. 30 seconds was enough. It was enough to get us across that threshold for moderate activity. Okay, so we had, this is what we knew at this point. We had energy expenditure for young adults. We had it for children. So we know that development is age related, but not age dependent. We understand from a product standpoint the speeds that they were being produced for kicking and throwing. We had process. We had process for throwing. We had the developmental sequences by Robertson and Halverson, 1984, and then later work by Langdorfer et al., including Robertson, that carried this forward from a longitudinal standpoint. And then for kicking, oh, right. So we didn't have kicking. And we actually needed to change our direction a little bit here, take a pause before we could move on to an evaluation of product and process, and actually come up with the process for the process, which was developmental sequences for kicking. So with a heavy lift from a few of my friends on this one, what we did was we took a step back and we wanted to take a look at what we knew already from a developmental sequence standpoint. So work by Deitch and Gessel, Hayward and Getchell, Lees, Roberts and Metcalf, Seefeld and Harmenstricker, Wickstrom. We consulted experts. And we took a large sample, 255 children, ages 4 to 11 years old, from all over the U.S. And we applied our hypothesized sequences. You can see here how they were broken down. There was levels between 2 and 5. And what we wanted to do ultimately was see cross-sectionally what these look like over time. Excuse me, cross-sectionally within time. So this is the approach. Here in the upper left, we're looking at somebody who actually didn't approach at all. They just stood behind the ball and they would swing their way. So there's no approach. For the individual here on the lower left, this is someone who just ran in a straight line behind the ball. They ran to the ball and kick in a straight line, and then you have an angled approach here from somebody. This for American football would be the typical kickoff or the field goal, where your individual would take a couple steps back, a couple steps to the side, and you would take that same approach from the side. From a support foot standpoint, here on the left side, what you'll see is somebody who's reaching. There's a nice gap there between the toe and the ball. On the right-hand side, you see somebody who is aligned. The foot actually disappears behind the ball. For the reaching, you also would code that's the same way if the person had stepped so far beyond the ball that there's a gap between the heel and the ball itself. Okay. For this next one, we're going to use the same picture to talk about both the trunk action and the knee action. The trunk action in this case, if you think about the developmental sequences for throwing, and you turn them upside down. So the hips actually here are open to the screen. You can see, essentially both sides, the ASIS on both sides of the pelvis facing the screen. And if you watch the video for this individual, you'll see that the hips close. It's a differentiated rotation where the torso is moving at a different rate of speed than the hips themselves. And that helps elicit the stretch shortening reflex and increases momentum and velocity. And then from a knee flexion standpoint, we're going to throw a line in here. This line goes right through the lateral side of the middle of the knee. And we're looking to see if the lateral malleoli is actually above or below this line for the highest level of kicking. In other words, was there flexion involved there? Okay, surface selection. So for surface selection, did we use a toe? Did we use the instep? Did we use the laces, the inside of the foot, the outside of the foot? Ultimately, did we use a toe or did we not use a toe? We're going to talk a little bit about this here in just a moment about why or why not this was something that appeared later and the importance of that. And then last, the follow through. These are just two different follow throughs. On the left-hand side, we have somebody who's hopping. So that is their plant foot. They left the ground. They landed back on the same plant foot. On the right-hand side, you have somebody who was leaping, somebody who took off from one foot and landed on the opposite foot. Okay, so ultimately went through our data analysis for all of those pieces, and we came back and we wanted to actually go through some of these results and combine them. In this case, for the follow through, we merged levels 3 and 4 because it was not statistically significant that we needed both levels 3 and 4. For knee action, ultimately what we did was we had 5 different levels, and we wanted to combine them. So we merged levels 1 and 2, we merged levels 4 and 5, and ultimately we ended up with this nice curve. Ball contact was ultimately removed outright. And so if you think about it this way, if you approach a ball from an angle, you would need to actually, excuse me, dorsiflex the ankle to be able to make contact with your toe. Something that just we never saw in all of our conditions. We actually never saw that. Excuse me. So ultimately, we never saw somebody dorsiflex their ankle and take an angular approach. And so what we were able to do then with our data analysis is remove ball contact for reasons like that, where we didn't see the association of one condition along with another one. It was no longer statistically significant. Okay, so here's what we're left with. We're left with a nice, everything has a 3 levels all the way through, and we're able to move on here. So now we have what we needed. Okay, so we have what we needed to be able to look at both product and process for energy expenditure, or against energy expenditure. And ultimately what we wanted to do was look to see contributions of product. In this case, it would be speed and process. So we had process scores from both throwing and kicking at this point to see which ones contributed most greatly to energy expenditure and see where that put us. So just briefly here, what we're looking at is ultimately our group. I wanted to show just a couple of things here. The first one is our ages. I mentioned them previously. So we have young adults with an average age of 23. We have children, prepubescent, and an average age of 8. We have the MET results here. This is published in the paper, so if you want to take a little bit closer look at it. But again, we have some significant differences here between the average kicking speeds and the average throwing speeds. I apologize to my international friends and colleagues that this is in miles per hour, but you can see the significant difference here in the results between the older group and the younger group, which is to be expected, of course. So first of all, just the correlations, the R values here that are related to this, and what you see here in the adults and then below in the children is that the process and product oriented or results here are related. It's 0.6 in adults, a 0.7 in the children, and so that's expected that these two things would be related. People who move with more degrees of freedom are going to produce higher yields in terms of velocity and so forth. So that makes sense. And then you can see that relationship there in adults is still moderate for the 6, the 12, and the 30-second intervals. And then in the children, you can see that those numbers, as you work down that first column there, are much less significant as you work through 6, 12, and 30. And I have to give all the credit in the world to my co-author, Till, whose idea this was, who did a lot of this work, and paper isn't produced without him, from the standpoint of taking a look at this in a slightly different way. And what we want to do here is actually look at these components together. So often we look at two things, just bivariate. We're looking at METs against product and METs against process. And well, what about a visualization of all 3 on the same graph? So we can do that with a response surface analysis, and that's what we have here. And this is no data. This is just an example, so that we can have a conversation. So on the right, what you're looking at is if there was no data in the model at all. Okay, so this is our base level graph with zeros. On the left-hand side, on the in the upper quadrant there, what you're looking at is 2 main effects. Okay, so if you had a main effect for both motor competence and speed, or excuse me, product and process, this is what we would see. Okay, so we would see a diamond shape. On the lower left quadrant, what you're looking at is process oriented. So that graph would be what we would expect if we had a main effect for process, how we actually move. And then in the middle there, so to speak, is a main effect for speed. And that main effect for speed would be something that we would suspect if we're looking at the product orientation there. So I'm going to flip back and forth between these screens, okay, so that we can take a look here at the adults, right? So as we look at these graphs here across, we have the 30-second condition on the left, we have the 6-second condition on the right, and obviously the 12-second condition in the middle. And so let's just flip back real quick. Which one does this look like? Does this look like a main effect for both? Does it look like a main effect for product? And does it look like a main effect for process? All right, so let's flip back again and take a look. And what we see here is that the graph on the right-hand side for 6 seconds, where we have the highest intensity of energy expenditure, is most aligned with the main effect for process-oriented results. So in other words, how we move. Are we taking large movements to produce these results? And then obviously, as we become less intense, there's less of a relationship there. There's actually a little slant there. It's kind of hard to see. And then we take a look at children and we see much more significant differences between these three graphs as the slope increases, because again, we have more skill variance, we have more product variance between the adults and the kids. And as you go back and look at the correlations and the numbers that are associated with them, I think this ultimately just provides a nice illustration of the main effect of process and how important movement and movement quality is to how we produce energy. But it also begs a question here as well that says, well, wait a minute, as we move and move well, these are higher skilled individuals. The individuals who are moving larger, with larger ranges of motion, with more degrees of freedom, are producing higher levels of energy expenditure, and that goes against Bernstein. That goes against what we understand about efficiency. And David Anderson brings up that question at the end of our talk today to talk about exactly what this means in general, where our next steps should be, and where should we go with this research, and why it's important to promote these things in interventions and with our practitioners, that doing something that's a continuous activity like running and walking, though it's great and has benefit, and there's nothing about what my research says or what I want to say that says we shouldn't do those things. But if we're skilled and we're competent, and then we add in confident, and we can move bigger, and we can produce higher speeds and better product, then ultimately we're producing higher levels of energy expenditure, which is a better bang for your buck. I get more out of doing this. All of the benefits that we wish to promote from a standpoint of healthy weight status, you actually get more bang for your buck for being more skilled, which couples with the fact that you'd probably be more aligned with doing the activities themselves. So where do we go from here? What's the next step? Well, some of my colleagues, notably in this case, Ryan Hulteen, brought up in one of his, actually right here in Journal Club, because he was in the Halverson Award winner last year, one of the Halverson Award winners last year, that there should be a look into cognition with assessment. He proposed the thought that there could be a throw catch task in which the individual themselves produces a throw, and they have to make affordances and change where they move, how they throw, the speed, all these wonderful aspects of it, and that leads to cognition. What about decision making, right? So I wanted to tease this just a little bit, because I can't wait to see everyone next year in Belgium. I can't wait to see everybody in person and shake hands and listen to all the great research that's happening all around the world. And I'd love to help get you there. So by all means, please submit an abstract and find yourself there. And in this case, this is just a little bit of a teaser of what I hope to present next year and next summer, as a little bit of work that we did this last summer as a leapfrog or the next steps to this research. And so what we did, we took a Stroop task, we took the throw catch task, we combined them, and we wanted to see what happened with decision making. So what you're going to see here is taking the lab. So what we try to do in a lab is emulate what's actually happening in an ecologically valid environment, what's happening outside, and that's really hard to do. It's really hard to to do that in a way that's meaningful, that's translatable. And I think we did that to the best of our ability with the research that I've previously presented, but this becomes the next step. So if you're playing a game, whether it's soccer, football, depending where you're from, or baseball or basketball, what might happen is you're going to receive a pass, right? You're going to receive a pass. You're going to pick your head up. You're going to decide, we're going to shoot this ball. We're going to dribble into space, or we're going to pass it to somebody else. And is that pass to somebody else? Are they open? Okay. And so I can't control that pass consistently if I'm the one producing it. So I want to use the throw catch task against the wall here, because the individual themselves has to control and self-regulate that own pass to themselves. So then they receive it and they have to make a decision. Is that teammate of theirs open or not? Right. And so in this case, there's an arrow. There's an arrow pointing to a wall. This is the second half of the Stroop task. So they're going to throw either congruent or incongruent. You'll see this summer what we did at the time, and hopefully we've got some next steps here moving forward in terms of decision making and the complexity of it. But these are the first steps. So let's just go ahead and play this. Okay, and so they're going to take a ball off the wall. They're going to see the arrow. They're going to make a decision to throw as hard as they can. In this case, in alignment with the arrow itself. They're free to throw and catch however they see fit. And then in this case, we also did kicking. So receiving the ball off the wall, aligning their decision with the direction of the arrow, playing it as hard as they can. There we go. All right, so the idea with this is to elicit some discussion, hopefully tempt you to come to the University of Ghent in our next meeting next summer. I hope to see everybody there. I hope that this work is accepted so that we can present it and have a nice discussion on some of these pieces here. And what I'd like to do is actually just talk a little bit here at the end of the presentation. I'll try to answer some of the questions that some people asked regarding this a little bit before I close. But before I do that, the most important thing here, I led with thanking individuals who help me write. In this case, I need to absolutely thank my support system at home. This is my wife, Allie. She is my emotional, psychological, financial, personal, instrumental, informational, moral, and loving support. And I absolutely wouldn't be here right now if I didn't have her with me for all the things and all the other things that are not listed as well. And these are my two children. This is my 1-year-old Ryder on the left and my 3-year-old Becker on the right. If you don't have an opportunity to have children, interact with children, find ways to teach them, to coach them. They are our future. And as a now motor developmentalist, I have learned so much from interacting with children in ways that I didn't think, actually, I think the best way I can put this is that there's so much more that I've learned outside of a textbook and off of a screen by interacting with them every day than I think I would have ever learned in the classroom. So I encourage everyone to interact with children, whether they be your own family or in the community, to help foster the next generation. So with that, questions. Well, here's the odd thing. I guess I have to just remember some of these questions in general. And I think there was a few questions that talked about the cognition, the next step, and where to go. And there's some affordances that we're able to make, and there's some things that we haven't yet been able to address. And ultimately, I'm in a small institution. If anybody has an opportunity that they know of to help finance some of these things, I would absolutely love some help in grant writing or finding them in terms of answering these questions. Jane Clark asked the question, how do you go about doing this? And where do you come with your next questions and so forth? And I love that question because sometimes I don't know the answer to that, to be honest with you. But it starts with you. It starts with the work that you do, that you publish, that you go to presentations with. I love interacting with individuals in the motor development world and all of research. because it inspires me. So I encourage you to continue the work that you're doing, and thank you. I'd love to collaborate with you if there's ever an opportunity in the future, because it's just a passion of mine. And then the next part of that is you have to have the tools. You have to look around you and see what you do have access to. And in my case, I don't have a lot. I don't have a lot here in my current institution in terms of tools. But I do have a wonderful support from my department, from my previous mentors, from my current mentors, um, in terms of asking these questions. And so that's the next piece of the puzzle is what do you have, what can you answer, and then what is the question, or where are the gaps, right? And so what I've been able to do in the past and how that leapfrogs to the next piece was an inspiration from my peers. Um, what don't we know? What do we need to know? What is that next piece? And then how does that align with what I've done? And in this case, we now have a better understanding of energy expenditure related to discrete motor skills. We have a better understanding of product and process and how that relates to energy expenditure. But there's so much that was still left unknown. And the ecological validity to what I was doing with just maximal velocity or maximal effort with velocity in a lab doesn't necessarily translate. So the next question is how I better translate that information? And then what about decision making, and how does decision making go into that, right? So our highly skilled individuals, the answer to those questions, does it relate to energy expenditure when they're in a game environment, or in this case could move the game environment into the lab itself, and where do we go from there? And so forth. So I'm in the middle of analysis of this next piece of the puzzle. I'm looking forward to presenting those results and answering some of those questions. And all along the way, I've got so many more, which is the point of this lecture, to show that there really is no straight line between two destinations. Sometimes you're left off and going in different directions, and ultimately that really enriches both what we know, what the world knows, and ultimately, I think what you do every day. And I just want to take one last moment to thank everyone for this honor, for this award, for this opportunity. Um, I know at this point, looking at the names that are on the list of previous winners, that I don't get to stop. I need to keep going because it seems like everybody else on that list certainly did. And thank you all for your inspiration and mentorship that has led me here and continues looking forward. So thank you.